in your book. I strongly recommend you go look at those and read through those and understand those. Now let's broaden our understanding of energy. So far we had the just kinetic energy and potential energy. And we said, if you recall, if we only have work due to limited things, gravity only, then kinetic energy plus potential energy equaled 0. But what about if we have other kinds of things happening, not just gravity? Then we see, and this is exactly how it happened, they started to see that, well, that didn't equal 0. It equaled something. It was not 0. It was not 0. It equaled some other value. And so literally what they did was they said, okay, well, everything else that that isn't balancing this, that's not kinetic energy, that's not potential energy, we will call internal energy. So essentially internal energy is whatever else we see. So we'll read what it says here though. We consider total energy of the system, which includes kinetic energy and gravitational potential energy and other forms of energy. Not all changes are accounted for by the change in kinetic energy or the change in potential energy. The change in energy can be accounted for in terms of internal energy, U. So U is internal energy. This is internal energy. All other changes are lumped together in internal energy of the system. All other changes are lumped together in internal energy of the system. That's like literally how we define internal energy, is everything else that's not kinetic energy or potential energy. So like kinetic energy and potential energy, internal energy is an extensive property of the system, as is total energy. So this is an extensive property, and energy is an extensive property as well. Change in internal energy in a process is delta U, which again is the internal energy at the second position minus internal energy at the first position. Final minus initial. Specific internal energy is symbolized by a small u. So capital U is internal energy, small u is specific internal energy. And if you remember the tables, or go look at the tables in the back of your book, internal energy is one of the properties on our tables. So now when we look at the change in total energy of the system, so E is energy. So change in energy, delta E, equals the energy at 2 minus the energy at 1, where we end minus where we start. And so what that change in energy for a closed system, again, this whole chapter is about closed systems. We will later see with open or control volumes that we have some more things going on, but the total energy of the system, delta E, equals the change in internal energy plus the change in kinetic energy plus the change in potential energy. And so this is what we call our energy balance equation. And we start with this. When we're looking at this, if we don't have kinetic energy, if we don't have potential energy, then those terms go to 0. If we don't have internal energy, then that goes to 0. Okay, so energy transfer by heat. So we've had, we talked a little bit about this. I put it out of order, but here is where it really goes. So closed systems can interact with their surroundings in ways that cannot be categorized as work. For instance, if a rigid container of gas is heated on a hot plate, the energy of the gas is increased even though no work is done. This type of interaction is called energy transfer by heat. We use the symbol Q. On the basis of experiment, beginning with Joule's work in the early 1800s, we know that energy transfers by heat are induced only as a result of temperature differences between the system and its surroundings, and occur only in the direction of decreasing temperature. So our heat transfers from the hot surface towards the cooler surface. Perhaps open your window tonight and see, it is winter in Minnesota, see which direction you feel that the heat is transferring. But that would be an open system. This is, we're still talking only about closed systems. Anyway, little side joke for those who live in Minnesota. Okay, sign convention, we saw this, but I'm going to say it again, probably again and again and again. But sign convention and notation and heat transfer. So also, we had this out of order with work, but again, heat transfer is the amount of energy transferred across the body in heat interactions with the system surrounding. Heat transfer into the system is positive, and heat transfer from the system is negative. We'll use this convention throughout the book, and to avoid confusion later, you'll see that the direction is shown with arrows. You'll see that when the time comes. The amount of energy transferred by heat in a process, heat transfer, is given by Q equals the integral from 1 to 2 of delta Q. The limit means from state 1 to state 2. Do not refer to the values of heat at those states. This is not temperature. Sometimes we have to really emphasize that. It's related to temperature, but it's not temperature. Heat transfer and temperature are completely different things. And this integral is not Q2 minus Q1. The net rate of heat transfer is denoted by Q dot, so the time rate of change of Q. In principle, the amount of energy transferred by heat Q during a period of time can be found by Q equals the integral from T1 to T2 of Q dot dt. Heat flux, which is the heat transfer rate per unit of system surface area. The net rate of heat transfer Q is related to heat flux Q, capital Q dot and small q dot, by the relationship Q dot equals the integral over the area of heat flux dA, where A is the area of the boundary of the system where the heat transfer occurs. The units on Q are the same as on W, kinetic energy and potential energy. They all have the same units. SI units, Newton meters or joules, and US customary foot-pounds force or BTUs. Heat transfer modes. See the book animations A7, tabs B and D. So based on experiment, evaluating energy transfer by heat, two basic transfer mechanisms are conduction and thermoradiation. In addition, empirical relations are available for evaluating energy transfer involving the combined modes called convection. The posted notes have more information on this as well as the textbook. But that's